And this one is Dr. Yuri Petnev's session. And I would like to invite Dr. Yoshiro Azum to take the chair. And I would like to request Dr. Yuri Petnev to take the dais to give exciting ideas about understanding light. And Dr. Yuri Petnev, MSc in Physics and Novosibirsk State University, Russia in 2008 to 2010. Sir. Sir. PhD in Physics, Hamburg University Berlin, Germany in 2010 to 2014, and postdoctoral researcher at Hammerlodge Zentrum Berlin, Germany, February 2014 to June 2015, and postdoctoral researcher at Helmholtz Zentrum Berlin at PTB, Germany, July 2017 to 2021. And he has a lot of work experiences in research assistant and research intern, and attended the NESY Winter School in Neutrons and Synchrotron Radiation, Austria, and assistant lecturer at Humboldt University Berlin in Germany, and presently working as visiting assistant professors, Department of Physics at BITS Pilani, KK Birla, Goa campus from August 2023. Sir, the mic is to you, and we are ready to listen your voice.
Double? I don't need double. You can hear me now very well, I hope. So, thank you for introduction. Thank you to organizers and especially to Professor Naik for inviting me there. In this place I'm already second time. Probably some of you met me already 2 years back. And today I chose a very simple talk, actually. Simple but complicated. People are thinking about this over decades and centuries and many thousands of years, actually, even before Christian birth. And the topic is light. Nowadays we see light. Here, light is there, light is there. Everything is because of light, right? But how do we come to this point that we have light? And the main question for me still, which I'm asking since many years already, what is light? Everything is light. Your telephone connection is probably light. Electromagnetic waves is light. I'm heated, I'm very much sweaty today and so on. I'm a black body radiation. I'm emitting light to you, but we cannot see it, unfortunately. So light is everywhere. But what is light? And we will try to go through the journey, but I still do not have answer. Right? We will start today with ancient views of ancient philosophers. How did they understand the light? Then we will talk about how the light is created. The model is actually very simple. And then I will tell you about the powerful light sources, probably the most powerful people built ever in the planet, the synchrotron light sources and free electron lasers, briefly only, and tell you about a fascinating experiment we did in Berlin, where I worked in Physikalische Technische Bundesanstalt, which is related to steady-state microbunching. And then I will tell you about a very simple gamma quant. What is spin of the photon? I'm asking these questions to a very famous big physicist. Always I get the answer, it depends how you see on it. We do not know. I absolutely do not know. Probably it's something third in reality, and the humanity will require another maybe some hundreds of years to understand this. What is light? I'm asking this question all over again and again and again. But we are using it. We are fantastic users of light, right? Now, let us talk a little bit how we understand how the light is created. And life is simply created. You take a charged particle, put a force on it, apply the force on it, accelerate it or decelerate it or bend it, it will radiate. As well as you can talk about atoms, change the energy level, then it will fall down and radiate you the photon. Right, the principle of many, many things. And nowadays, we have thermal excitation, which is like light bulbs. I don't know, modern children probably never seen such a light bulbs with a filament. When I was a child, it was all over common light bulbs with a filament, black body radiation. Nowadays we have LEDs, completely different spectrum. Nowadays we have LEDs here, RGB, right? We have also various gas lamps. As well, if you go to the sea, you will observe that there is a chemiluminescence, bioluminescence, fireflies, and many, many, many other things. A lot of glowing things in nature as well. And all of this is just due to charged particles changing the state. Probably. Right? And now let me talk about the particle accelerators, which is my work actually. I spent a lot of years working for this. I will give you a little bit of brief introduction of what people are doing and how they are generating the light. Right? Nowadays, there are existing such called synchrotron light sources, which are accelerators of electrons, which basically circular machines or linear machines. Synchrotron light sources are usually linear machines, and they are the size of a stadium or something like a football stadium, right, with a circumference of maybe 400 meters or smaller around this area. Right? There are many facilities. One of the biggest from Japan is sitting Professor Azuma. He knows it very well, which is 8 GeV machine, one of the most powerful energy machine. We know what is GeV, what is electron volt, how much energy electron gets by passing 1 volt, and G is giga. Very high energy for electrons. Right? There is a ESRF in France. There are 2 accelerators in Germany where I was working, which is BC2 and MLS, which have variable small, from small energy of 50 MeV you can get at MLS to 1.7 GeV you can get at BC2. And these machines provide you different spectrum of the photons, different wavelengths, depending on experiment you want. They can give it from visible to X-rays. And of course they are mainly optimized for X-rays, very powerful X-rays, which are used for different experiments. Before we had a talk about coronavirus. Coronavirus was measured in synchrotron light sources. You bring the molecule, you bring the virus there and measure it. How do we know it looks like corona? Thanks to synchrotron light sources. And many, many, many other more applications are there. And I will not take a breath from Professor Azuma, who will talk about this tomorrow. How do we use them? But roughly there are 70 synchrotron light sources in the world. There are existing few in India as well. One of the biggest is RRCAT in Indore, which has Indus 1 and Indus 2. There are as well existing linear machines, which are free electron lasers. Those machines are usually optimized for the very, very short pulses and the so-called peak brightness. Right, they're giving you short pulses of very, very bright things. For some applications, this is not even useful because it will just destroy everything. It's too powerful. But there are applications where they are very much used. There are maybe 15 to 20 FELs in the world, but around 100, so of the powerful FELs, and maybe around 100 in total. And the FELs probably are the brightest light sources ever created by humanity. Right. So now I want to tell you a little bit how those machines works and how we get the light. Let us talk about the small and simple metrology light source, which is a 48-meter circumference machine only, which has the energy from 50 MeV to 630 MeV. But the beauty of this machine, you can store the beam current from 1 electron, which is like 1 picoampere, to 200 milliamperes, which is a lot of orders of magnitude difference. And you can use this machine for calibration of different devices, photodiodes and such things. Right? Or sometimes people go to space and they build some detectors on satellites and they want to calibrate them. They bring it to there and calibrate it. Because metrology, why is it there? Because Physikalische-Technische Bundesanstalt, which is PTB, is a German national metrology institute, which is specially working for metrology. Right? So how does it work? If we look on the schematic of such machines, we see that the electrons begin actually from in this machine, so-called microtron. I will tell you how it works as well. And they reach energy of about 105 mega electron volt from microtron, and then they are getting injected to the main ring. And the main ring consists of different electromagnets, which are dipole, quadrupole, sextupole, and octupole. And there is as well, you can see U125 undulator. I will tell you what is it as well soon. And the different beam lengths. As I told you earlier, you need to apply the force on electron to radiate. And bending magnet is something which is bending it, applying the force. And when you apply the force, it will radiate, like a flashlight like this. And there is such a called device, which is a RF cavity, which is there to accelerate or to keep energy, to compensate the energy loss. Right? And a lot of diagnostic in these machines. So simple picture of a racetrack macrotron is you have thermionic gun, which has a hot tungsten cathode, which emits the photon, which emits electrons. Then electrons go to, you can see in the blue color there is a LINAC written, where they accelerate the energy, right? Immediately after LINAC, they will bend one turn. If you look closer in, can you see my, yeah, if you look closer in this area, they will bend immediately, and then they will accelerate once again, and then there is a dipole magnet, this huge thing is a dipole magnet, and they will follow the tracks. So they will bend in this magnet, then they will accelerate, then they will follow the next track. Because the energy is increasing, they will follow a longer distance. And then this will go until they follow through all the tracks. At the end, they will reach energy of 105 mega electron volts. And come to transfer line, and then they will be transferred to the main ring. In main ring, as I told you already, they exist in the magnets, different type of magnets. It's similar to what you have in optics. In optics, you have mirrors, and here we do electromagnets. And we know about Lorentz force. Right? If you have magnetic field and velocity, and you can get force, simple. So there are dipole magnets which are used to bend the beam, and there are quadrupole magnets which are used to focus the beam. And there are other sextupole and quadrupole magnets which are used to fight with second order effects, which I will not go details, of course. And those magnets were fabricated very nicely in my hometown and the institute where I was born, kind of, and did my PhD, no, not PhD, but did my bachelor and master, which was Butker's Institute of Nuclear Physics. And I'm still very much happy that I'm out of this area, because they gave me a little bit of education, which I appreciate very much. All right. Now, why do we build those machines? Important parameter is brightness. Brightness is how many photons do you get per the small area, per some bandwidth, right? How bright is your source? And here you can compare, for example, there is different on the scale. You can see average brightness. I don't know exactly at which wavelengths. But there is for comparison a candle, which is something like 1000. Our sun, 10 to power 10. And there are different generation light sources. First generation light source, which is only bending radiation. Second generation light source. And then there is undulator radiation. Undulator is a device which made out of magnets which are changing the polarity north-south, north-south, which makes the trajectory of electron going in a sine wave like this. And this will improve the signal of radiation by n squared. Right, well, you will get much more signal. And if you go, so we start with a simple radiation from bending magnet. It gives you a broad signal. If you go to undulators, you will get peaks. And you will get much higher, much stronger radiation. Right, and for many experiments, you want to have monochromatic. You don't want to have a broad spectrum. Chemistry people will know about this very well, and biology people as well. Right? So please visit talk from Professor Azuma. He will tell you how we use it, how he used it. He worked many, many years in Japan with not only in America as well, and he will tell how to do that. How much time do I have?
I think you have a few minutes plus question.
Few minutes only.
A few minutes, yes.
Okay, here I will quickly then flash the experiment which we did in Berlin, which was called steady-state microbunching. We did proof of principle at the experiment at the metrology light source. And the idea was from the long bunch, this is a long bunch, we want to make it with a structure, microbunch structure. And those micro, similar to free electron lasers, kind of, the people who will know. And if you get it microbunched, you can get intensity much more, which will be by the factor of n squared. So you will get coherent radiation out of this. These microbunches will radiate together. Classical effect, coherent radiation. How do you do this? Well, we brought the very powerful laser, which was like 1 micrometer wavelength, neodymium YAG laser. Then we had to shoot it together with the electron beam in the undulator. And we got energy modulation from the laser to electron beam. So we use light to modulate the beam to get the light back. Something like that. So we get energy modulation after interacting with the laser. And then the idea was that you need to set the optic of the machine, all the magnets, in such a way that when you come back, your beam, due to this energy modulation, will arrive with a perfect kind of microbunching structure. And this was the whole idea. And we did that experiment. This I will definitely skip. It was very demanding and difficult task. But we got the results. And this was published in a Nature journal. And nowadays is quite a good cited paper. And this indeed is a promising tool. Maybe it can be a future generation light sources. China is very much working for this. And they want to build it for lithography machines. This can provide you a very strong narrow-banded radiation, very powerful narrow-band radiation for lithography. And we know all about the chip productions, and there is a need for the different light sources. Okay, and then of course we will celebrate it with our team. After that you can see me somewhere. I'm always hidden behind, but somewhere there and maybe there. Here I'm not, but. And there are Chinese colleagues we work together, and the Germans. Importance of SSMB is, as I told you, is a future light source, which is very promising. I will skip this. And now I want to tell you one more promising experiment we started to do in BITS Pilani. last semester I was preparing for the lectures which were related to biology, people, introduction to oscillations and waves. And I came to a topic which was called biophotonics. For me, being a person who is out of completely different world, but being in BITS Pilani, and I was seeing which instruments we have. We have the optics lab, which have avalanche photodiodes, and people are doing some quantum measurements and things. So I came with idea that what is biophotonics, and let us measure. The very first experiment was we built the setup with a lens and another lens. This lens is focusing to the optical fiber, and there is an optical fiber which is connected to very sensitive avalanche photodiode, which we had in the lab, which is connected to the photon counting module. Simple, very simple, there is nothing more. And the whole thing is connected to computer. And then my very first experiment was to place in a black box the PhD student like this. Unfortunately, we couldn't measure signal from him. Our device was not sensitive enough. After that, we tried to do the plans. We went out of optics lab, collected the leaf, immediately brought it in the black box, and we got the results. Results were looking like a decaying signal, and this is measured in the visible light, exponentially decaying signal. Just we take the leaf, bring it to the black box, and it radiates over half a minute. Half a minute. We know from quantum mechanics and whatever, when you excite states, it's very fast. Here is slow process. And then the question, of course, we are not biologists, we don't know anything about biology. I'm very much afraid to tell that today, but I've heard that we have plant biologists, bioplants. Hopefully, some people will help me today to understand, and we can talk about this and discuss what exactly we measure. And in general, please visit a talk of my student, Tejas Kulkarni, who is here as well, and he will give a talk about our measurements tomorrow, right? And there were, of course, many questions. Is this reproducible? Are you really measuring something? And so on. After that, we started to shine different lasers on the plants, right? We tried with a flower. Somebody asked, oh, you should try with a flower. We tried with a flower, we don't get any signal. You require photosynthesis. We are measuring photosynthesis, right? And the decay constant of these signals will tell about how good is the photosynthesis in the plant, right? Maybe somebody can explain it well to us. Me from accelerator physics world, I am not expert. Okay, but I'm starting to learn slowly, I'm coming. We did a lot of experiments, so Tejas will tell you. We did statistical, we measured it many times, it's very much reproducible. We measured it after a few days. We measured different plants, different colors, different pigments, different many things. All of them give you different signals under different excitation wavelengths. Okay. So now I'm coming to conclusion. Sorry if I'm a little bit delayed. I don't know what is timing, but. So today I started my talk with very much philosophical views from people being a flashlight and every eyes. Then we came to the very powerful sources, and we discussed universal rule, how to generate, how we get the light from, where we get it from. And it's not only from electrons, it's from many charged particles actually, right? And then I told you examples of the very, very powerful light sources and very weak. Imagine now, when you go home, see on the plants and imagine that all of them radiate light. Isn't this amazing? For me, it's super impressive when I found out that every single tree, every single green plant is radiating light as well. We cannot see it, but it's there. And I'm still asking question, what is light? Maybe some of you will tell me later. Here I am done. Thank you for your attention. Questions?
Is there any questions? Thank you, Dr. Yuri Petnev, for enlightening us about light is form of electromagnetic radiations that travel in waves and behaves both as particle, a photon, and a wave exhibiting properties like reflection, refractions, and diffraction. So its dual nature and described by quantum mechanics underpins technologies like lasers, solar cells, and optical communication systems. Thank you, sir. And I would like to call Dr. Yoshiro Azuma to conclude this session with propose vote of thanks to the resource person.
Well, Yuri, thank you very much for your, well-organized and introductory pedagogical as well talk. And, I have been colleagues with Yuri recently at BITS Pilani, and it's been so good to find a good colleague like him, myself coming from Japan and him coming from Russia. And we have been together, we have been teaching the optics and waves course for freshmen. New experience for me, but it has been a very good experience with a good, really nice introduction by Professor Petnev getting involved in that. And in the course of the last few months, I've been even more impressed by what he has started, what he just told you about, this bioluminescence from green leaves. He just started it with ordinary, very ordinary lab equipment. Once he finds that, well, at BITS Pilani, well, it is difficult to do synchrotron radiation facility experiment or anything. Well, what he did was just get out of the labs and grab some leaves from nearby plants and measure the light emanating from them, which can be adjusted in many ways, but by illuminating them initially. And, well, just the bioluminescence itself probably has been known for some time, but this kind of complicated responses and interesting varieties of them, that has been completely unexplored, I understand. So, yeah, surprise, surprise. Well, he just goes out of the door and plucks some, he was just plucking any leaves to begin with. He, I think, is getting some hold on something at least very interesting, maybe even important. I congratulate him for that. Okay, and well, please join me in thanking him. Oh, well, any other question from, what about the students? You can ask anything. Yeah. You're so shy. Well, grab him when he comes down if you like to. Okay? And tomorrow I will give a talk. Oh yeah, yes, please. Mm-hmm.
Excellent presentation, very excellent presentation, starting from the basics towards the theory and then the applications. Highly impressive. Right? I'm talking about my work, a part of my work, a piece of my work, where we used cyclotron, microtron we used at Mangalore. That was a smaller 8 MV electron. We tried to see the irradiation of microtron on nanoparticles, functionalized nanoparticles, which were prepared using biological routes. This silver and gold, of course, Ravi did it. We happen to see that the shape changes. Particles diminish in size Plus the shape also, morphology changes.
Shape of the particle, of the beams
Yes,
itself.
yes, yes.
Yes, yes.
Zero nanoparticles.
Because you don't
That's
have
what-
reproducible source probably as well. Microtron is a one-pass machine.
Yeah.
When in synchrotrons you get the multi-pass machine. And
Yeah,
there is
yeah.
radiation dumping involved as well.
Accelerator.
And in a microtron you accelerate every time.
Every
Usually in microtrons what we do, we use it as a diagnostic.
Of course, we used here for our scientific.
No, if you go to Mainz in Germany,
Geomining, yeah.
they have very much experience and they have high power, high energy microtrons.
Yeah,
But they do, I'm not sure they use it as a light source. Microtrons is not as a light source.
Yeah, yeah,
Microtrons are as injectors.
But here at, I'm talking about, we have an establishment at Mangalore University. Down
Right,
south we have a Mangalore University. There the microtron source is there, 8 MB, and now they have even increased it too.
Right.
So all these experiments are carried out. And because he was working on nanomaterials, biofunctionalized nanomaterials, we had a scheme from BRNS, that is Nuclear Research Center. They provide research schemes for us.
There you
Yeah,
need to
yeah,
go.
there, you know,
Yes, yes.
yeah, when we were, they were also interested in knowing what would happen, right? So we happened to see the shape morphology changing. Particle size diminishes, morphology also changes. That's an interesting observation for us. Thanks a lot.
Right.
Thanks.
In India, if you want to use a synchrotron radiation, you should go to ERCAT. If you want to use a little bit more professional device, you go to other country. There are good collaborations with Japan. There are collaborations with ESRF. In Kolkata there are as well. Cyclotrons. Cyclotrons are there, I think. Right. Okay.
Well, thank you very much, everybody.
Thank you, sir. Thank you, Yuri Petev and Yoshiro Azuma. And now, I would like to invite Dr. M.K. Naik as a chair and Dr. K.S. Rane as a resource person. So, Dr. K.S. Rane will give us great ideas about abatement of the microbial and pharmaceutical pollutants in wastewater. And I would like to invite both of you to the dais. And I would like to introduce K.S. Rane sir very briefly. So he did PhD in IIT Bombay in 1976 and FRSC in London, and postdoctoral works in IIT Madras in 1976 to 1977 and Pune University. In 1977 to 80, Germany, UNESCO, DAD 1984 and 95, DAD 1992-95, and 2002 to 2004, UMIST Manchester. And he has very great teaching and administrative positions also. And he had awarded a law too, and a fellow of the Royal Society of Chemistry London, visiting professor of Washington University in St. Louis, and visiting scientist CSIR lab and Pune and Bhavanagar, silver medal of ISCAS and best paper award of ISCA and ITAS, and World Academy of Science, Engineering and Technology. London Invention Disclosure at Washington University in St. Louis, USA. Sir, the stage is over to you, and we are ready to listen your great voice.
Thank you very much for nice introduction. Thank you very much, Professor. You are my chairman here. Well, before we two stalwarts give very, I mean, it is impossible to understand sometimes such a talk. And mine is very simple one. It's not a rocket science. But at the end, you will understand this is also science. I'll try to put it that way. Okay. Yeah. Update it. Update it. Yeah. It's a simple thing. Water is the elixir of life. It's a medicine. Yeah, everybody knows about it. It is not just a poetic, it is biological, ecological, and philosophical truth. If water is the elixir of life, why must we purify the water? The core question now. Everybody in the house has a cant or pant or something like that. Why do you want to? If it is a medicine, take it, gulp it. Why must we purify the very elixir before drinking it? Next prize. Philosophically, yes, water is a medicine. Nature's essential self-purifying cycle that sustains ecosystem. That's why we are today here. Practically, into bracket India, in India, please note it, in India, that elixir now passes through contaminated rivers, aging pipelines, please note each and everything. These are all very important for us. Chemical runoff and urban pollution before reaching our tap. In other words, the elixir has been tainted by human activities. Okay, next slide. Next slide. Okay, there are root causes are there now. And most of you know also about that one. It's not a big issue. Pollution of natural sources, industrial waste, agriculture, chemical, all those wastes are there. Sewage discharge. Please keep it in your mind. If students are there, make a note. That enters rivers and groundwater, result biological and chemical contaminants in natural water. Urbanization and population growth, which we know very well, but that matters too much. Over-extraction of groundwater, and overuse of fertilizers. Rising hardness, nitrate and fluoride heavy metal contents in the water. Aging infrastructure. We didn't have infrastructure at all, but whatever we had, that is in the aging process. Leaky, I think Vranda should remember, I'll come to that one in Goa especially. Leaky, corroded pipelines. Everybody knows about it in the road, how, surrounding all the pipelines are corroded. And unclean tanks. Recontamination of even treated water. Though we are using a treatment, that itself is a very traditional old one. That itself, once it is treated, again it gets contaminated. Unequal microbial treatment, again. Outdated treatment plants are under operation, and that is too much in our country. They are not in operation, most of the, I'll come to that. Variable chlorination and microbial contamination. Climate stress, that I need not to, everybody knows about it. Irregular monsoons, droughts, floods, after all, water quality affects. Seasonal turbidity, stagnation, bacterial boom. These are the root causes. The next slide. The major contributors to the water quality impairment are ineffective industrial treatment, agricultural runoff, domestic waste, please note domestic waste, inadequate sanitation infrastructure, and urban runoff. Next slide, please. The inefficient or inadequate industrial treatment is very well, because we are proud of ourselves that we are the 6th largest in the world in chemical manufacturing. So we are great, no? But that greatness should percolate in our daily this one. We are 3rd largest in Asia, fine. 2nd largest in the world in coal mining, handling. 2nd largest in the world in steel making, fine, everything is fine. But why the hell you are making the water polluted? Yeah, next slide. Yeah, these are some facts are there. Again, as you know, government of India never accepts such things. Because government of India is always opposing anything, no, whatever is there, it comes to there, this one. The drinking water quality is measured as a part of the annual Environmental Performance Index, EPI. The high score indicates high quality. This much is how it has been measured, I don't want to tell. Now look at some countries like Ireland, all those things, Austria, all 90 plus. 90 plus, we are very, quality is very good. No doubt about it. And there are so many countries which have no that much quality. But look at the Indian EPI score is just 25.8. If you compare the Ireland with a 90 plus, do you think that we are drinking the safe water? And nobody addresses this one. The government does, of course. Today only I saw in the Deccan Herald, among 780 districts in India, only 4 districts are at par with some quality of water. One of them is fortunately in Karnataka, that is Gadag. That's all. Then what about others? Nobody bothers about it. Yeah, next one. The Environmental Performance Index, initiated in 2002 by the World Economic Forum in collaboration with the Yale and Columbia University. It was initially launched as an environmental sustainability index and was designed to be a tool for measuring and ranking the environmental performance of a country. Next. India's ranking in the Environmental Performance Index in 2024 is, we are 176 out of 180 countries. Nobody is addressing this one. We have see, we are sending the moon or so, everywhere we are sending. Fine, good. But what about the reality where each and every person has to be bothered about? The government of India has criticized. Always it has to criticize, no? Because you don't want to take the blame on you in front of the world bodies. Next slide, please. All over the world, also the following are the major contributors of the pollution of the water. Whatever I have given the industry, everywhere, all over the world. We may be saying that we are the 6th largest in chemical management. Everybody is having their own way of industrial revolution. Means everybody should have the same quality like us. But the figure shows that quality differs. So what does it mean? If that is so, then why the EPI score differs from country to country? When everybody is using the same treatment plan, there is no change in the water treatment plan. We started in 1800, sorry. Answer may be inadequate water purification methods. Next slide, please. Yeah, conventional water means students are not that many here. Everybody knows is a coagulation, flocculation, sedimentation, filtration, dispense. Everywhere, anywhere in the world, whether it is an advanced country or the not advanced, these are the norms for the purification of the water. World over, the above steps are followed. If so, why the Environmental Performance Index for drinking water differs from country to country? Next slide. Yeah, there are some countries which are having 90 plus quality, the index, and they are all, if you see scan the table, they are all using the same conventional method, but they have evolved themselves in some of the processes. That evolution is not there in India. Look at the last. India, only 27% of the urban sewage is treated. 27 means I am drinking the good water. Professor Naik is not drinking, and you are also not drinking. So water absolutely is a polluted. Yeah, next. It means the high EPI scoring countries have evolved the conventional treatment process with some advancement, while the low scoring countries have not. Yeah, next. Globally, water is broadly classified into 2 realms. This is a new thing for me. Water H2O. One is saline water, another fresh water. Earth reserves around 97.43% saline water, which is not drinkable, is a useless, absolutely useless. The major portion of water we have, H2O, the 97.43% is useless, not. The remaining is only 2.57% fresh water. Only 2.5. So next slide. Next slide. Out of 2.5%, which is reachable, only 30% is underground, which is not reachable. You have to go deep and impossible to get the pure. 69% is locked in the glaciers. You know, that is also not tap, you cannot tap it. And out of 2.5%, only 1% rivers and lakes. And that 1%, which is we call is a fresh water, it is contaminated. So where are you giving? Are you getting the water? Think more about it. Out of the 1%, industry consumes 4%, agriculture, the major thing, so they consume 73%. And we have to give them no water. And 11% evaporation. That is a natural process. And 11% to dilute the pollution. In Delhi, you have to sprinkle, no? You are creating the pollution and you have to sprinkle with that water. You go to any town, each person has got 2 or 3 cars, he takes that treated water and washes that one. So, next. So, scenario in India now. India occupies 2% of the world's land area. India represents 16% of the world population. And see, you are only talking about population. We never bother about livestock. We never bother. They also drink water, no? Any planners only thinks about giving a fresh water to a human being. And we never bother about the animals. India has just 4% of the fresh water. Of the water. Next slide. The annual utilizable water resources in India are 447 BCM groundwater and 690 BCM from surface water. Over 80% of the domestic water supply in India are served by groundwater. Next slide. Next slide, please. As per a 2015 estimate, tells that 80% of the India's surface water is polluted. It's not my figure. So don't think that I am threatening you. We're all getting threatened. Surface water is a lake and river and those things. And year 2025 estimate varies between 45 to 70, depending on some improvement is there in our country. Okay, next one. Shortcomings in the conventional water treatment process. Year 1804, the first concept of the purification came into existence. Since then, we have not changed anything. Same process going on. Now, everybody knows that, the city folks at least, they know that water is chlorinated. Sometimes you get the smell. Sometimes some lady says, my hair become brown or something like that. But you know that chlorination is not used by anybody for disinfection. I'll come to that one. Next. Next text. 21st century needs rethinking the water treatment process. Next. The conventional processes are designed to remove traditional pollutants. Again, I'll come to that one. That is the 18th century they started. The traditional pollutants are there, which can be treated very easily with the processes. But these days we have persistent organic pollutants. Industrial chemicals and pesticides. There is no treatment plant which can remove these things. Then pharmaceutical and personal care products. We are all using all those personal care, beauty, all those chemicals are going into the water. They are called emerging pollutants. There is no regulation in the world so far about the emerging pollutants. For other things, there are regulations. So how much is there in the water, nobody knows. Then microplastics, as you know, this is the worst thing is going on now. And heavy metals. Next. Added to these emerging pollutants, dealing with microorganisms in water is challenging due to diversity, resilience, and difficulty of both detecting. We cannot detect also. What are the pollutants in water? We can't detect. There are no tools. There are no tools about that one. So if you don't know, you are drinking. Water is clean. I am drinking. That's all. Next. Flaws in the conventional chlorine disinfection. It is a very important thing. Chlorine reacts with the organic material in the water, even trace amounts, forming harmful disinfection products. These are carcinogenic. And all water, there is an organic material. No water is free of organic material. Even a trace of organic material, and your chlorine you are dosing like anything, because in our treatment plant, he doesn't know how much dose we have to put, he doesn't know. So he puts a lot of chlorine and it does this job. And we don't have any detection, how to detect all those people. We don't know. Next one. Flaws in conventional chlorine disinfection. Not foolproof in removing all the pathogens. Now you are talking about it. So it's not making free of pathogens. And as you know, there are many pathogens which are now inorganic compounds react with chlorine, thereby increasing the demand for Cl2 because they are putting a lot of chlorine. Not optimum what is there. And reducing Cl2 effectiveness against pathogens. So this all vicious circle is there now. It's a vicious circle. It's not that I bring in house a Kent and give that. Not the solution for us. We have many poor people. Next. Chlorine disinfection not for the next one. Okay. No, that's what I'm telling you. No. No, he's asking me whether all those pathogens can be. We don't know which are the pathogens present and removing is. Okay, that is the problem. That is a big problem. We have laboratories, but these are all in the nano size. E. coli is the normal thing, just to study. Okay, I'll come to that one. Conventional water treatment do remove the organic matter and microbe, but not completely. Alternate methods is adsorption and membrane. That's what our Kent, all those things are. You cannot put the Kent in the municipal water and supply to you all because those membranes are very expensive. Very expensive. You can't afford. Even at home also, every year you have to put 6,000 or 7,000 rupees for changing that one. So impossible. There is something hopeful, that is advanced oxidation processes. Here where I have a little bit research work there. With giving all those bad things, at least there is something. Next please. Biological treatment are not effective due to stubborn pathogens erupting due to human activities, as pathogens are classified as readily biodegradable, slowly biodegradable, non-degradable, and non-degradable soluble. See, these are the classes, different classes we don't know. First of all, we don't know about the pathogens out there, and all those things that are very stubborn. And which method you will put? There is no method at all. Methods like ultraviolet irradiation can be done, but you cannot put in the municipal water where you are supplying millions of liters every day. Ozonolysis also is there. In a small place, we can do that one. Chemical treatment with the H2O2 also same, again is very expensive. Heat and steam treatment also expensive. Next slide, please. Next slide. Yeah. There are advanced oxygen processes which most of the countries are now following. Which can remove most of the organic materials, but organic molecule bonds will be broken by this one. And some microorganisms also. AOPs, that is advanced oxygen process, are either ozonization, or you can put H2O in that one, or ozone and UV, or use a photocatalyst, or you can use phantom processes. There are processes are there. Again, they are under research level now. Some countries have adopted those things, but it will go long way. But the problem remains that whatever I told about pollutants, they are all there. You have to find out a way to remove them. Yeah, next. Photocatalysis is our main process to mitigate organic pollutants and microorganisms. Next, please. Photocatalysis, I don't know where my chemistry people are there. So you take a semiconductor. Now the semiconductor world it is now. So when you take the electromagnetic waves, whatever Petne was telling, then you will excite the electron from the valence band to conduction band, and they react with the adsorb oxygen and adsorb moisture, and radicals are formed. Radicals are formed. That radicals are very easily they degrade or break the organic bonds. Okay, next. Okay, now for simple college people also can do this job. I want to remove color from the water. Color molecules in the water. So I use the methylene blue, which are simple, methyl orange, methyl red. As such, if we keep, there is no degradation, there is a slight decoloration takes place. But if you use some catalyst, you see that depending upon the catalyst and nature of the catalyst, you can decolorize. You can decolorize. So whatever the water, the color is there, you can remove it. Simply, otherwise there is no other way. Next one. Yeah, next one. Next one. Next. Next. Okay. You know, I don't know, poultry farms are there. Poultry farm, I think how many people are non-vegetarian, I don't know. But in the poultry farm, they use steroids, prednisolone, and they inject the chicks. So prednisolone is for fattening. It fattens. Once it has reached 1.5 kg, they kill it. And now, no doctor is there to give the prednisolone. And these people, to make it fast growth, the poultry farm person put lot of prednisolone, and remaining is discharge. And if you see the water flowing from the poultry farm, it is full of steroids. And that goes to the water bodies, and my water treatment plant cannot do anything with that one. So you are consuming. You are consuming. This is all sickening. But at least in Germany, I have seen the stall where chicken, it is prednisolone free. But in our country, nobody knows first. Then when will you make the free? Okay, next. Oh, 1 minute. Yeah, 1 minute. 1 minute. Go back. There is one physics persons are there. Yeah, physics. Yeah, he knows my problem. Yeah. Now, you know, your dress, if you keep in the cupboard, it doesn't fade, no? If you sit in the house and wear there, it doesn't fade. The moment you go out, it fades. Correct? It fades. It means degradation takes place. Now question is that in the sunlight, the free radicals are formed. Those free radicals will degrade the material. If it is not degrading in the dark, why? This is what my research area now. You understand my point? It degrades. No, any bright dress when you are wearing, you go outside, it fades. So in water, if I had to use a catalyst, and it does the job in the daytime, it does, if at all. If my observation is that even in the dark also it does, then my catalyst is for 24/7. No? So that is my way of looking at. So I see that the TOC, total organic carbon decrease, with a different catalyst. In the sunlight, the above one, they are 51, 71, 72%, whereas in the dark it is less, naturally. But there is a degradation. There is a degradation. Why it degrades? I have done little bit EPR studies, I don't know, EPR studies, electron parametric resistance studies, and I find that even in the dark, there are radicals are formed. Next. Next. Yeah. In the dark, whatever these organic materials, they are adsorbed on the surface. Those organic materials are giving electrons, naturally all electrons. Those electrons now reduce the metal catalyst. If it is Fe3, Fe plus 2 or MO plus 5, all reduction will take place. And this reduced form is produces this oxygen gets adsorbed on those reduced elements and take that electron and radical is formed. So radical mechanism also is possible in the dark. That is my evidence through the EPR. Yeah, next. Now, why metal oxide degrade organic matter? I told the reactive oxygen species are there. Next. Yeah, microorganism. This is okay for removing the color or organic matter. How they will kill the microorganism? I had done, I think Varanda is there. She is a part of the work of that one. The zinc oxide prepared by different ways show different nano size particles and which have got high nano size or low nano size. No, low one, less than 38 nanometer. It shows the inhibition zone maximum. Means they can remove the microbes. They can remove. And this is well proved also. Next one. Some E. coli you are telling, no? E. coli you are telling. Even some of the oxides, iron oxide, zinc oxide, titanium, all those can also remove some of the E. coli. Next one. Why the metal oxide kill the microorganism? Why they kill the microorganism? Reactive oxygen species are formed, generated on the metal oxide, cause oxidative stress on it. ROS, yeah. Next one. Yeah, this is something. So it also can be understood. Yeah, next one. Yeah, then one can study BOD, all those things. Next. Yeah, next. Next, okay, it's repeated, okay. Now the thing is, I have a running project. I'm not just like that freelance scientist, freelance journalist like that. Freelance, I'm not a freelance. I had to do something. Yeah, I have a medical college in the Hubli project. Many medical doctors had submitted, but I was there during COVID time. I wrote a project and submitted, and they found mine is something. So we are doing some work on hospital water contains lot of drugs, and that they are sending to sewage treatment plant. As you know, sewage only 27% of the sewage is treated. Now say it is a good sewage plant. Now it has no possibility of removing these newer polluters. Yeah. So the water goes into the effluent of that sewage, then it goes in the garden. And they are telling that we are using that water for gardening. Fine. Without microbe or something like that. Then that water percolates. There are many bore wells are there around, or many wells are there. That water goes and percolates there, and all those microbes are there in the water. So it's a big. So when I said I will remove those things, and that's what I am doing that work with the photocatalysis. Next one. Yeah. Yeah, I use some amoxicillin, tetracycline, paracetamol, all those things. Next. Yeah, we got some award also in ICMR. Next. Yeah, now the Professor Venkatraman. Now hospital, in a hospital, I have some 5 minutes. Okay. In the hospital, we know that there are drugs taken by patients. We know. There was 100 different types, and those are there, fine. How much is there in the water, we can't detect. But how many are there, at least we can. What I did, Nanda, you can also, what I did, you know TLC, I took a drop of water from the wastewater, that water, and put on the TLC. Then, depending upon the organic moiety, it should start moving. You know, to study that one, I did something about the movement of the organic. It is a methylene blue, methyl orange, methyl. Just I took those things. Now, I know that they are moving. If I put all three together, in the last trial, all 3 bands are there. 3 bands are there. Now all those 3 bands means I know that in the mixture of my water, there are 3 different organic materials. Maybe 4 are there, but I have put only 3 are there. Now what I did, the TLC, how many of you have worked on the TLC, I don't know. The TLC plate, I coat it with the titanium oxide or with the zinc oxide. They are known photocatalysts. So when I put the drop on that one, drop should not move. That is the 2 things I can see. First of all, I found how many are there. Second, how many are killed. And I can use that catalyst for the purpose. Yeah, next. Next. Okay, next one. Now I'm doing something still better. I use amoxicillin, prednisolone, doxycycline, then aspirin. I'm trying to. I think it is a simple chemistry. People may laugh at me. Yeah, we don't know. Yeah, people may laugh. Kya kar raha hai? But okay, something may come out. Who knows? And people like this, if you invite, I can bark this one and make you all bothersome about that one. So that will, okay. Thank you very much. Yeah.
Dr. K.S. Rane has given valuable ideologies about microbial pollutant abatement in wastewater treatment uses microorganisms like bacteria and fungi to break down organic pollutants, and while pharmaceutical removal involves advanced processes like ozonation, membrane filtration and activated carbon adsorption, and techniques such as bio augment and constructant wetlands enhance efficiency, removing up to 90 to 90% of contaminants. And thank you, sir. And I would like to invite the chair of this session to conclude this session.
Yeah, let us give Professor Rane a big hand for his wonderful presentation. Morning I had mentioned about how much agriculture produce you are producing. It is almost 353 million tons of cereals and pulses, and then about 350 million tons of fruits and vegetables. But at what cost? By pumping about 60,000 tons of pesticides into the ecosystem. And that's where you find your water is otherwise water is elixir of life, sanjeevani of life, but it is no more a sanjeevani. What water we are drinking here, God only knows, isn't it? But there are some techniques available. In our own laboratory at Raichur, when we were there, we know there is a laboratory which determines the quantum of E. coli present there. And especially during that time, when water was released by the Municipal Corporation of Raichur, almost in that particular year, as many as 17 people died of cholera. And that was attributed to the presence of E. coli in high number. And the number of E. coli were 6 times more than what is recommended by the WHO. So that's why the techniques are available. Only thing is they have to be further maybe streamlined or strengthened on a large scale so that it should be available for rural area also. So thank you very much. Are there any questions? I am not asking the audience. Yeah, please hurry up because I have to catch a train by 6 o'clock. Right? Doctor, I have to catch a train at 6 o'clock.
Yes, sir. It's a quick question. It was a great talk, sir. So at Bangalore, we are working on safe grey water concept. So we are promoting urban gardeners who are growing the vegetables on terrace and balcony and all to reuse water from washing machines and all. So we are developing sustainable cleaning products like fabric wash, dishwash and all. So what is your thoughts on the water contamination due to detergents? There are many sulfate, phosphates, bleaching agents. So one best example is Bellandur Lake in Bangalore. The foam, the amount of foam generated due to the detergent. So just insight on the detergent which causes so much pollution and the need of what are the alternative ideas to overcome this pollution, sir?
Yeah, I think we will thank Dr. Rane when she is, quite around 75 years of age, but speaks and almost talks as if he is 35 years. He is as young as 35 years. Let us give him a big hand. All the best to you, sir. Thank you.
Thank you, sir. Thank you, Rane sir and MK Naik sir. Thank you very much. And we would like to move towards the next session. So actually, we finished the tea, so that's why also just we do not take any tea break, and we will have to continue the session. And now I would like to call Dr. Shreyashi Basak for as a research person, and Dr. Vrinda Borkar as a chair of this session. And I would like to invite both of these two. And now I would like to give a brief introduction about Dr. Shreyashi Basak, and MSc in mathematics from IIT Kharagpur, PhD in statistics and statistical inference of directional distributions from IIT Kharagpur, and worked as research associate, Department of Computational and Data Science, IISc Bangalore. Also worked at BIT Mesra and Ranchi and Jharkhand as Assistant Professor of Statistics at the Center of Quantitative Economics and Data Science. And she published a lot of papers and presented a number of papers in various conferences, national and international too. And madam, the time is over to you, so you will have to address us with a great word on your topic of bootstrap analysis in hypothesis testing.
So good afternoon everyone. I am Dr. Shreyoshi Bosha. So it's not. So most probably I'm the first one who is will be talking about some mathematics and statistics related topics. So my topic will be on first I will discuss what is ANOVA. So ANOVA is generally used when we want to compare the means of 3 or more groups. And in this case, the testing of hypothesis is, null hypothesis is whether the means of all the groups are same, and alternative hypothesis is at least one mean from the two groups differs. So the one-way ANOVA model is defined like this, and where mu is our grand mean and tau I is our treatment effect and epsilon ij are random error, which is generally taken to be normally distributed as mean 0 and variance sigma square. So to testing in ANOVA, we generally find some kind of total sum of square errors, and then we split it as between group sum of errors and within group sum of errors, and after taking the degrees of freedom between groups and within groups and dividing by the degrees of freedom, we get the mean square error of these two groups. And after taking the ratio of these mean square errors, we get a test statistics which is distributed as F distribution, and after calculating the test statistics, we take the null critical hypothesis, critical value as our from tabulated F distribution, and if our test statistics is greater than the critical value, we generally reject the null hypothesis in this case. So here is one real data example. If we take 3 groups of test scores of 3 teaching methods, and there is a small example I have taken, and we can find the between group sum of squares and within group sum of square and total sum of squares of the 3 groups test scores. So after dividing by the degrees of freedom of the within groups and between groups, we take the mean square errors and between groups and mean square error within groups. So after taking the ratio of these two mean square errors, we take the F test statistics, and after that we can find the critical value of the F statistics from the table of the F statistic value, and if our test statistic value is greater than from the critical value, so we can reject the null hypothesis. But for this example, our test statistic value is less than the critical value, so we are failed to reject the null hypothesis or having the equality of means of these 3 groups. So to apply ANOVA, so this some assumptions should be made. The assumptions are independence of the observations, normality of the errors, and equality of variance across the groups. So what happens if some of the assumptions are not made? So in that case, our research problem comes. So we have our major research is on statistical inference and testing of hypotheses on the directional statistics. So directional statistics is where the observations are not on the Euclidean space, and whereas it is defined in the circumference of a circle, of circumference of a sphere, or some manifold. So these are some usefulness of circular data. So if we plot this in a rows diagram instead of linear histogram, it is showing there is a periodicity of the data, whereas in the linear histogram the periodicity on this is not taken care of. So so plotting the linear histogram in such kind of data set, it will not be useful, it will not be a good diagram for this kind of circular data sets. So these are some examples of circulate data, clock data, compass data, and some direction of birds flying data. So to represent circular data, we can represent it by a zero direction and orientation. And normal arithmetic mean is not a sensible measure for this kind of circular data. Circular data can be represented by a unit vector in the q-dimensional hypersphere, and also it can be represented by q1 minus angles. And these are some this is one of the important distribution in spherical data, which was invented by three research scientists, Fisher, von Mises, and Langevin. And this distribution is, in short, it is called as ABML distribution. So in our research, we have taken this distribution, and the density function of this distribution is given by equation number 1. And we have taken the ANOVA problem of this distribution. In this case, we cannot say that the errors are normally distributed, and the equality of the variance parameters are not met. So in this case, we cannot use the F distribution like in the normal case. So in this case, we have developed a likelihood ratio test for testing the equality of means of different groups. So this is our adaptive likelihood ratio test. And we have developed a particular bootstrap algorithm to test the hypothesis of this problem. And another test is some non-parametric bootstrap test. So this research is mostly kind of theoretical research. So this is another test we have developed, like permutation test, and this is the test already proposed in the literature. So we have compared our test with this test if it is already proposed in the literature, and we have developed different kinds of bootstrap algorithm for finding critical values of this kind of test. So next is we have also proved some theoretical results, so I am not going into the details of these theoretical results. And this is some numerical aspect of my work. So we have compared the test at size values and power values of our proposed test and of different bootstrap algorithm. And this is the power curves of our algorithm. From the diagram, we can see that the red curve is the power values of the non-parametric bootstrap test. And we can see from the diagram that this red curve, non-parametric bootstrap test, has a less power than the parametric bootstrap test. So we can see that non-parametric bootstrap test is not so much useful in this kind of data sets. So other good two tests are parametric bootstrap test and the test already proposed in the literature. So that two tests will be useful for testing the hypothesis of equality of means of several groups. So we have made some packages. So if anybody is interested of seeing the programs of these codes, so they can see the GitHub page of mine, and these are all programs are already uploaded in the GitHub. So this is some robustness investigation of our data. So if we consider contaminated FBML distribution, and if we apply on our test on that contaminated distribution, we can see that the loss of power values are very less. And if we just increase the contamination of our data, the power value will be decreased. So this is the last application of our test to a real data set, and we have considered a data set which is denoting the measurement of remnant magnetization made at 4 different locations at a place in Australia. And the data were given in the notation of theta and phi. And first we have fitted this data set with the FBML distribution by chi-square goodness of fit. This is the QQ plot of the 4 data sets, and from this plot we can see that all the data sets are from FBML distribution. So next we have tested that whether the concentration parameters are equal or not. So from the test we can see that the concentration parameters are not equal. So we can see that the original assumptions of the ANOVA is not met here. So we can apply the bootstrap algorithm here, and after applying the bootstrap algorithm to our developed bootstrap algorithm to this kind of data sets, we can see that the p-values of the test are almost all are greater than, for all the tests it is greater than 0.05. So we can see that for all that the null hypothesis, we cannot reject the null hypothesis of having the equality of the mean source of magnetization. So this is the usefulness of our developed algorithm. So in this work, we have also developed the, in case of other than the simulation study, we have also developed some mathematical proof of our bootstrap algorithm. So that is why it is it has been published in a very good journal. And so we have also established the asymptotic accuracy of our proposed test procedure, and also it has been published in another book chapter. So this is my last conclusion, and this is, so I have finished in a very short time. So if anyone is interested, then she can contact me, or she can contact me. And okay.
Thank you, madam. Shreyashi Basak has given a great idea about this bootstrap analysis is a resampling method used in hypothesis testing to estimate the distribution of a statistic, example mean and variance, by repeatedly sampling with replacement from the original data. This approach helps assess the variability of an estimate without relying on strict pharmatic and assumptions, making it robust for complex data sets. And thank you, madam. And now this is the time to So since Shreyas Bhasak madam is leaving today, so that's why also just we would like to felicitate her, and I would like to call all the teachers and the resource persons to the dais. Principal madam and Dr. Venkatraman sir, please felicitate her.
ಹೌದು ಇದು ಫೆಲಿಸಿಟೇಟ್ ಆದ ನಂತರ ಅವರು ಕನ್ಕ್ಲೂಡ್ ಮಾಡ್ತಾರೆ.
And Shilpa madam, please honor Shreyas Bhasak madam. She has given such a wonderful talk about these statistics, and this one is really a great thing for us. And thank you, madam, for giving a great thing to us. This one is really the memorable time for us. Thank you. Thank you all. And now we would like to conclude this session. So our chair of this session, Dr. Vranda Borkar, conclude this and give the proposed vote of thanks to the resource person.
Last session of the day, and Dr. Basak, young scientist in the field of statistics. What I would say is the research is very deep, and it is a theoretical research, very difficult research, and definitely all in the hall, we should bless her that her progress in research goes on and she shines as a very good researcher in the coming years. Thank you.
Thank you, madam. Thank you, madam, for your sweet voice. And this is the time to get the entertainment. And our students are ready to perform several patterns of dances. And at first also just they are ready to give the Bharatanatyam and then Yakshagana. And after that, our normal dance. And, and please, all of you to be here and get entertainment.
ಸಿಂಚನ